All right, everyone. Thank you for joining us. And my name is Fabio Anzà. I am a research assistant professor at the University of Washington in Seattle. And I'll be discussing in this kind of set of 4 lectures, I'll be going through, I guess the underlying theme is the use of differential geometric tools in quantum mechanics. But the goal is to kind of help students and people, anyone really who is interested in this sort of topics, to get more familiar with the actual structure of the state space of quantum mechanics, of quantum systems, and in particular for finite dimensional quantum systems. Now, the reason why the focus is on finite dimensional quantum systems is obviously, first of all, they're kind of a bit easier to study because it's a finite number of degrees of freedom. And the second one is that if you look at the modern development that we are seeing in the past, 20 years especially, I mean, it's obviously started way, a long time ago, but in the most recent 20 years, it has accelerated dramatically. Then obviously, there's a lot of interest for understanding the physics of finite dimensional quantum systems, because these are supposed to be the underlying mathematical tools that we're going to use to study and leverage quantum computers. And, trying to go a bit beyond the actual paradigm of quantum computing, the goal is to kind of, oh, hey, Francesco, you're back.
Yeah, sorry, my internet just...
No worries whatsoever. I decided to kick it off. So trying to go beyond the paradigm of quantum computing and kind of looking at this whole emergence of the kind of this new wave of quantum information technologies, and at the center of this is the understanding of finite dimensional quantum systems, and in particular their non-equilibrium behavior when there is a lot of these systems involved. So I'll be addressing this kind of topic as a whole and talking about complex quantum systems, but really in this context, the word complex, which has been misused a lot of times in this particular context, what I really mean is many-body quantum systems, and outside of the realm of equilibrium physics. Now, obviously, this is a school and it's intended for students. So we'll focus on kind of the introductory material. And so we'll go through very basic examples and kind of simple analysis. But the idea is to get the student more familiar with this set of formulas, so that she or he can go on and do their own analysis. Or, if you're interested, you can obviously reach out if you like these kinds of topic and you want to collaborate on a project. I'm more than welcome to discuss. So let me start sharing my screen so I can kick it off. Just double checking that you're seeing my iPad.
Yeah, it's perfect. Thank you very much.
All right. So I'm going to begin with a little bit, and this will be kind of a bit of a slow lecture, in the sense that I want to be sure that the topics are kind of introduced without jumping anything. And I remember that when I first studied quantum mechanics, and I had no idea of what the actual modern research topics like quantum information and all of that were. So I'm going to try and go through very basic examples that don't really require a lot of advanced math or advanced understanding, but we'll have this kind of constructive approach moving into this new territory. So there is I listed here a bunch of 6 crucial references that I've used, not necessarily to prepare the lectures, but to have this, to kind of learn about this geometric approach to quantum mechanics. And I want to be, I want to give a little bit of very brief historical account. So to my knowledge, one of the first person to make this connection between the use of differential geometric tools. So first of all, the use of geometric tools to understand physics is not, obviously, it's not new. One can actually argue that the best understanding that we have today of classical mechanics, or at least the mathematical structure and kind of the foundation, is indeed geometrical, and it's given by symplectic geometry. Symplectic geometry is a very broad and wide mathematical area, but for us physicists, the idea is that symplectic geometry is basically what dictates what gives you the rules of the behavior in phase space. And as most of you know, and probably all of you know, phase space is simply when we have a finite dimensional system and that has a certain configuration space, and we're looking at its evolution in time. And so the way this is typically set up mathematically is that we look at the space, at the configuration space, and at all the possible ways in which a system can change its configuration space, so the space of derivatives. And obviously it's a little more subtle than that, but that's the idea, that once you go into this space and you try to understand what are the relations between the configuration space, so the situation the system is in, and the way it can change, there are very precise rules for how a physical system can evolve in this space. And so this is historically, this was regulated by Lagrangian and then Hamiltonian mechanics, but then kind of over the years, what we understood is that basically symplectic geometry is really at the core of all of these theories. So the first one to make this, to my knowledge, to make this connection explicit was Strocchi. He was an Italian physicist who wrote this review, Complex Coordinates in Quantum Mechanics, in 1966. And you can tell right away by reading, it's very accessible. And you can tell right away that, when you look at this way of framing classical and quantum mechanics, their difference, which is usually, usually quantum mechanics is explained and it's given in stark contrast with respect to classical mechanics. But really, the funny thing is that if you actually look at it carefully and with some detail, you realize that the underlying rules that dictate the way a quantum system evolves in time are really not too different from what happens to a classical system. Now, I really, I'm not going to mention all of these references, but I do want to mention this book. So The Geometry of Quantum States is a wonderful book by Bengtsson and Zukowski, and it's beyond the actual relevance for the geometric tools. It's a wonderful book about quantum mechanics and about the physics of quantum systems. So I really I highly advise people to look at it, and it has wonderful introductory sections. And I use it for my own research because it has all the basics figured out. Before we actually get into the material, there's a funny historical account that I learned recently. So apparently Dirac, realized, because Dirac was a mathematician So he had projective geometry in his training, and in particular complex projective geometry, which is, as you will see in a moment, is really the mathematical structure underlying the quantum state space. Because he had this in his training, apparently this was the language, projective geometry and complex projective geometry was the language that he used privately for his own calculations, even for infinite dimensional quantum systems like in quantum field theory. But apparently, and this is actually a historical account by a historian of science, but apparently he constantly decided not to make this choice popular. And so what he would do is that he would derive his results in the language of complex projective geometry, but then rewrite everything in the language of linear algebra, because according to him, this was easier to understand for most physicists. While as a mathematician, for him, it was easier to look at this geometrically from the perspective of complex projective geometry. And I wanted to start with this account because a lot of time when you try to do something, when you try to introduce a new formalism, there's always a little bit of a pushback about why is it necessary to introduce a formalism that is non-standard and kind of it's not the road usually taken. And so typically the perspective is that there must be a reason. Now, the reason that I agree with this, but it's also, I think there is a lot of value in trying to look at the same thing from different perspectives, because this gives us a better understanding of what that thing is. The actual motivation for why I believe that one should learn at least a little bit about these topics is that, as I mentioned in the beginning, we have new challenges. We're in 2022, and there's a worldwide effort towards trying to kind of be able to exactly manipulate huge sets of quantum states. And this comes with challenges that involve hardware, that involve software, that involve applications, that involve theory. So in general, a much better understanding, a more comprehensive understanding is going to be needed. And indeed, there is a lot of research that is going on. So I'm not claiming that this is kind of like the only kid in the block. Absolutely no, by no means. But I do think that this approach has been underutilized, and it provides a lot of, or at least it did for me, it provides a lot of clarity in thinking, and it provides a lot of useful tools that you can then build on to provide new tools and to solve new challenges that we're going to have to face no matter what. All right, so this was kind of my overall introduction. And so, I forgot, if you have questions, Francesco, Leah, and Camille are probably kind of looking at the chat if somebody is asking, but feel free to interrupt me, feel free to ask questions. If this can be an interactive session where people ask questions and kind of develop this together, I would absolutely love that. Before I actually, sorry, Francesco, I saw you were.
Participants want to ask questions, raise their hand, and I give you immediately the right to speak. No problem. Yeah, thank you.
Thank you, Francesco. Yeah, so the last thing before we go into the material is, again, this is, I'm going to be presenting very basic stuff, very introductory stuff, but this is part of my own research. So I actually, this is I'm very invested in this. And so if you're interested in general, if you like these topics, and if you if you want to either work on it or if you want to know more, do not, feel free to contact me. I do want to say for students, there is plenty of room for, kind of introductory projects, more computationally oriented one, much more theoretical one. I mean, this is it's a wide space, and I think there is a lot of interesting things to do. So if you're looking for small projects, I'm more than happy to chat about anything. All right, let me get into the basics, into the actual material. So I'm going to start from very basic quantum mechanics. So the way standard quantum mechanics works, and when I say standard, I mean the standard formalism of quantum mechanics, is that this is built on top of three crucial objects, mathematical objects. The first one is a quantum state that belongs to a Hilbert space, right? So the way this works is that we're going to assume that the Hilbert space has finite dimension. And this means that you can always find an orthonormal basis, which means this is a set of vectors EI. I goes from 1 to D with the following properties. EI EJ is equal to delta IJ. This is the first one, and this is called orthonormal. I mean, it's the property of a basis. And then there is the following EI is equal to the identity. So this property, so I have no idea, how much, I don't even know who the participants are. So I don't know how, how much of this, of all of this is already known. So I apologize to the more senior people, because this is very basic stuff, but I think it's very important that we go through that. So the completeness basically is telling you that you're not missing anything. This is the identity over the full Hilbert space. It's telling you that when you take into account this number of D orthonormalized vectors, you're not missing anything from your Hilbert space. Your description in terms of EI is complete. And then once you have that, a generic psi is just sum over I1 to D, psi I EI. And all right, this is first one. So first topic, state. The second are observables. So observables, and this is, I think this is highly underappreciated. Observables in classical and quantum mechanics have two roles. First one, they are the thing that we measure. And in this sense, the way quantum mechanics deals with objects that we measure is through so-called self-adjoint operators. So an operator is self-adjoint when you define the adjoint in the following way. If I have any two state psi, actually, let me write it like this. You can compute the scalar product between psi and an operator, a linear operator on phi. And this has to be equal to the following, a dagger phi. So this is a self-adjoint operator that, and when you write it in a basis, this means the following, that you write EI A E J. This is matrix element Aij, and then you know that Aij has to be equal to a Ji star, where star means complex conjugate. So as I was saying, there's a twofold role in observables. And the first one is that, again, they're the things that we can measure. And of course, as many of you know, the way this quantity it's interpreted is that this is the expectation value of A. So if I do many measurements, the mean value that I can expect to emerge from this many measurement is going to be described by this quantity. So this is the first role that they play. The second role that they play is as generators of transformations. Again, usually these two things are, for example, in classical mechanics, they are very much one and the same, in the sense that any observable, you can use it to define some kind of transformation. In quantum mechanics, things are a little bit different, and this difference will emerge in the geometric formalism. So this as generator of generator of transformation. And for example, you know, the observable, the momentum is the generator of translation. So if I do something like e to the I p alpha p, then this basically takes my state from some x into psi of x plus alpha. All right, so this is the second part, observables. What is the third part? Is dynamics. So how is dynamic usually kind of dealt with in quantum mechanics? And obviously is the famous Schrödinger equation in the most kind of in the simplest form, and it's written in the following way: H psi, where H is the Hamiltonian, of the system. Now, this so these are the three objects, the three kind of building blocks of quantum mechanics. There are states, there are observables, and there is a dynamic. Now, this is obviously quite different from the way we usually deal with classical mechanics, because classical mechanics deals with phase spaces, right? So the way we usually set up the classical system is that we say that, you know, like a particle, it has a position and it has a momentum, x and p. And so what we do is that we set up a space in which this is x, this is p, you know, and a system kind of evolves with some dynamics, evolves in this space. So the picture is actually quite different from Hamiltonian mechanics. But what I want to convince you today is that this is actually not true. So before I do that, let me remind you that kind of a little bit of classical mechanics. If I have a classical system with a classical Hamiltonian H, which, you know, as you can take to be like the free particle plus some position-dependent potential. The way the dynamics is set up is through Hamilton's equation of motion, so that we have x dot is dh over dp, and p dot is minus dh over dx. And I wanted to make this explicit because it's going to be important, because these equations will come off of Schrödinger's unitary dynamic, which is something that for me was, when I learned it first time, was actually very weird. And I thought that the geometry of the evolution of quantum systems was actually very different from the geometry of evolution of classical systems. And it turns out that this is actually just not true, in the sense that there are really a lot of analogies. All right, so before going to the details of the relation between classical and quantum mechanics, let's have a look at and actually forgot to say this, but most of this material, at least for today, but a lot of the examples later as well, will be focused on the case of a qubit, which is a two-level system, so that the Hilbert space has dimension d equal 2. Just because, well, first of all, it's easier, but the reason why it's easier, it's actually very important. And it's not just easier because we can diagonalize things and there is not a lot of them. It's also easier because we can visualize the whole state space, and it's going to be very important that we do, and we'll get familiar with this construction a lot. So what is a qubit? It is a two-dimensional quantum system. So I have two quantum states. So my basis, EI, it's going to be the set of bases. I'm just going to call it 0 and 1. And this means, from the prescription of the Hilbert space construction, that a generic state is of the form C0, 0 plus C1, 1, where C0 and C1 are complex numbers, right? Now, this is true for states states in Hilbert space, but because of the probabilistic interpretation of quantum mechanics, basically there are redundancies in this description. And the way these redundancies manifest themselves is in the following way. First of all, if I multiply my state by a whole phase, e to the I phi psi, nothing changes. And the reason why nothing changes is because the kind of the bread and butter of quantum mechanics, as I said before, are expectation values. And so if I have a self-adjoint operator, and I have my experimental friends in the lab, they're actually making measurements, and I'm doing the theory behind this measurement. These are the quantities that I'm computing, where A is some self-adjoint operators. Now, obviously, this is, if I do this, e to the I phi, this is a scalar, so it just gets away. So there is no, expectation values are not sensitive to this change in the phase. However, again, because of the probabilistic interpretation of quantum mechanics, this is also true if I multiply my Hilbert space vector by an arbitrary real number, like 3 psi. Now, obviously, if I do this, my expectation value is just going to do 9 psi a psi. And this obviously, it has no physical relevance, because it's just a factor that gets multiplied every time I make a slightly different choice. The important point here is that while physically these two operations have no meaning in the sense that they identify the same physical configuration, mathematically this is not true, because obviously this 3 psi, it's a different vector. I'm multiplying all of its components for number that is non-zero, and so I get a different vector. So these are actually different mathematical states, but they're not, they identify the same physical situation. What this means is that the Hilbert space is actually not the state space of quantum systems, but it contains the state space of a quantum system, in the sense that there are some relations that we need to impose on this state space to uniquely identify basically the states of a quantum system. And synthetically, I've talked about multiplication by a phase factor and by a real number, but obviously you can put them together into a unique complex number, lambda, with some modulus and and some phase. And so the general requirement is that you can multiply a state psi by some complex number, let's say lambda psi, and you're going to get the same physical situation. And this is a relation that we need to impose to actually find the state space of quantum systems. And we're going to do that constructively. And then I'm just going to mention the generic results for arbitrary dimensional quantum systems. So let's do it constructively for a qubit, right? All right, so we have psi 0. This is equal to C0, 0 plus C1, 1. We said that we can always multiply by a real number, right? So what do? We take our generic state, and let me just, to emphasize the dependence, let me just call this psi of C0, C1, right? So to emphasize the dependence on C0 and C1, I made this explicit. And of course, because we can always normalize, we can always multiply to an arbitrary real number, I just, for any of this psi 0, I just compute the quantity C0 modulo square plus C1 modulo square. And this gives me some number that I'm going to call lambda tilde. And so obviously, if I take psi, I can multiply it by 1 over square root of lambda tilde. And I'm going to get C0 divided by square root of modulus C0 square plus C1 square, 0 plus C1 square root of C0 square root of lambda tilde psi square plus C1 modulus square 1. There you go. And now, obviously, I'm just going to call this C tilde 0, 0 plus C tilde 1, 1. And then you get that C tilde 0 modulo square plus C tilde 1 modulo square has to be equal to 1. Right? So this would be nice because it would be a sphere if the quantities C tilde 0 and C tilde 1 were real numbers, but they're actually not, right? That we said that they belong to, they're complex numbers. But there is one more relation that we can use to uniquely identify the space of a quantum system, and it's the phase redundancy, right? We have used multiplication by an overall real number, and now we need to use multiplication by a full phase if we want to uniquely identify the state of the quantum system. And so the way this is done, there are actually many slightly different ways to do this. The way mathematicians do it usually is that they take this psi, they write it as a vector big Z, because this identifies homogeneous complex coordinates, and this is usually identified with some Z0, Z1, and you say that this is equivalent to basically 1 Z1 divided by Z0, whenever Z0 is different than 0. So basically what you do is that you push everything to the second part of the vector. This is not what we did today, but formally it's exactly the same thing. I'm just going to mention it because, in the literature, especially in the mathematical literature, these are the transformations that you're going to find. And I don't want you to get confused because this is actually, it's exactly the same thing. So the way we do it is that we choose, we write C tilde 0 as modulus of C tilde 0 plus a phase that I'm going to call E phi 0. And so psi, after getting multiplied by 1 over square root of lambda tilde, it's also going to get multiplied by the opposite in order to cancel this phase, right? So this is going to be e to the minus I phi 0 divided by square root of lambda tilde psi. And when we do that, we're going to find the following relation, that the new psi is going to be basically some modulus of C tilde 0, 0 plus modulus of C tilde 1 e to the I phi 1 minus phi 0, where I've introduced C tilde 1 is c tilde 1 modulus e to the I phi 1. 1. And now what you have is, let me call this, now this is positive. This is positive, but it has a phase. So the whole thing, so this is basically an independent complex number. And this is just c tilde 0 is a real number that basically counterbalances the complex number and ensures that you have normalization. Now, all within this picture, all the possible c tilde 0, c tilde 1, modulus of c tilde 0, modulus of c tilde 1, and phi 1 and phi 0 are allowed. But obviously, you know, the way we understand the manifold, the structure of the state space, is by putting coordinates on the system. So by choosing a way to basically uniquely identify these numbers, c tilde 0 and c tilde 1. And there are two major, well, there's one major way in the literature, and is the construction of what is normally called the block sphere. Block sphere. So the way this is done is that you realize that because of c tilde 0 modulus square plus c tilde 1 modulus square has to be equal to 1. This is like the construction of a sphere. Actually, I mean, this is not necessarily needed because the mathematical construction is already there. So you can, you know, if you have enough knowledge of math, you can just realize right away that this is the construction of the so-called Riemann sphere, which is the same thing as the block sphere, just, you know, different literature, so different nomenclature, but the idea is the same. So what you do is that because you have this this relation, and now these are just positive numbers because we have uniquely selected the moduli, you just write it in the following way. Psi is cos of theta over 2, 0 plus sine of theta over 2, and you put a phase here, 1. So they're uniquely, and again, so let me just check that this corresponds to what we had done. You know, this number here has to be larger than 0, and this is why we're using theta over 2 and not just cosine over theta. So in this way, basically, you have that theta belongs to 0 and pi, and theta over 2 belongs to 0 and pi over 2, so that we're only in the sector where cosine and sine are positive. And the sign essentially of this, because remember, as a complex number, this can have a phase. It's handled by its unique phase phi. And when you write a pure state for a qubit like that, you can easily see that a pure state represents a point theta phi on a sphere, because obviously you have cos theta over 2 plus sine squared theta over 2 is equal to 1, and phi is a generic phase. So the way this is represented on the sphere is the following. Let's say that this is my coordinate system. This is let's see, this is y, this is x, and this is z. Yes. So this is my coordinate system inside the sphere. This is the xy plane. And so you have two coordinates. One is basically the angle from the xy plane, and this is theta. So I'm just gonna identify this the following way. This is the point. So this is theta. And obviously, you can choose some arbitrary 0 where to start your phase, and we're just going to choose this to be x. And so this here is phi, right? So you have two coordinates, theta and phi, that uniquely identify the state space of a quantum system. And again, this is about what I was saying before, that the reason why dealing with qubit, with a single qubit, it's easier. It's obviously because, you know, there's the dimension is small. There's only two orthogonal vectors, so it's just easier to deal with the linear algebra of this quantity. But I think that actually a lot of the reasons why we understand qubits much better is because we can actually visualize, because the state space can be embedded in 3D, which is where our intuition works at its best. All right, so this is one way, and this is the standard way. I mean, there's a Wikipedia page on block spheres, so it's a very popular. It's kind of the bread and butter of anyone who does quantum information theory, but really anyone who does research on quantum mechanics of finite dimensional systems. Now there is a slightly different way. Obviously, this is not the unique parameterization that we can use, right? There's a slightly different one, and that I'm going to introduce, and it's the following: square root of 1 minus p0 plus square root of p e to the I phi 1. And obviously, you know, it's very obvious what I did. I just took cos of theta. Actually, I just took sine of theta over 2, and I just call it square root of p. Right, because sine theta over 2 has to be larger than 0 and smaller than 1. Then we get that p is between 0 and 1, and phi remains the same, right? 0 and 2 pi. So the way I call this the block square, and the way this is represented is actually as a square. P and phi, and so p is between 0 and 1, and phi is between 0 and 2 pi, and so a generic point here is the pair p and phi. Sorry, need to use the same phi. There you go. Is p and phi. Now the reason why, obviously, you know, this is while the parameterization is different, we're obviously describing the same space. Now, the reason why these coordinates are important is because they basically p, we know the probabilistic interpretation of quantum mechanics gives us directly an interpretation for the quantity p, which is just the probability that if I make a measurement on state either 0 and 1, then I get as a result 1 with a probability p, right? So the probability, if I'm in state psi, of getting as a result of the measurement the state 0 is 1 minus p, and the probability if I'm in state psi of getting state 1 is just p. There's another reason, there's a geometrical reason why this quantity, these coordinates, the p phi coordinate or the probability phase coordinate, are very, very important. And it has to do with the dynamics, and this is what I'm going to do now. And this is actually kind of as an introductory topic. It's the last one that we'll cover today. So
sorry, Fabio.
Yeah.
There is a raised hand. Can you just allow Jean? You can unmute yourself and ask your question.
Hi, yeah, sorry. So here with the block square, if I'm looking at this, so it seems to me that the bottom and the top lines can be identified. So we have a topological cylinder, but that's distinct from
with this, you mean?
Yes, exactly.
Yeah. So no, you're absolutely right. So I'm swiping under the rug a lot of stuff. Yes. So this point and this point are actually identified, right? So it's wrapped. So yes, you're absolutely right. And it's more than that. In fact, I mean, we know that there is a sphere representation. So it's not just a cylinder, because it's not just as these two lines that have to be identified with each other. It's slightly different, is that this line here actually doesn't exist. It's not a line, because when P is equal to 0, the phase is not well defined, right? So if P is equal to 0, my state psi is just 0. And so if I multiply by a phase, I just get the same state, right? So, right? So this line, so strictly speaking, the coordinate in differential geometry language, the coordinate patch that I'm using holds for P in 0, 1 interior. Then I have P and phi. But then when P is either 0 or exactly 1, then I basically have 2 points. So the way geometrically, the way you can understand this is that think about the square as an actual, you know, like an A4 sheet. Now, like you suggested, if I try to identify the top and row line, I get a cylinder, right? But if I want to implement this idea that the lines, the P equals 0 line and the P equal 1 line, they're not lines, they're points. After I close the cylinder, I also need to squeeze the outside circles into a point. And that's basically up to deformation, that's a sphere, right? So I'm closing, I'm taking my sheet, closing it as a cylinder, and then squeezing the two circles around it, and that's a sphere, basically.
Okay, thank you. Yeah.
All right. So
perfect.
No. I think it's a very important point, and the way, I mean, the kind of one sentence answer is that the notion of distance that you have on this space, it's highly non-trivial. And as we'll see in the next lecture, this is actually a very important point, because it's a very important point of departure between classical and quantum mechanics, because quantum systems have a very strong, in the sense that it's a very important notion of distance between their states, while classical systems don't necessarily have that. So this is something, you know, the notion of distance that we have on this space, it's not up to us. It's I mean, it is what it is, and it's defined. It's the so-called Fubini-Studi distance, and we'll cover it in the next lecture. So we'll see that actually the geometry, there are a lot of subtleties. But the reason why I wanted to start introducing this set of coordinates is because it makes very clear the connection between classical and quantum mechanics at the level of the geometry of the evolutions. And the reason is the following. So I have a Hamiltonian, and let's say that my Hamiltonian, I have already diagonalized my Hamiltonian, so I know exactly what its eigenstates and eigenvalues are. So I can write it, I can always write it like this, 0 plus E1, and this is the so-called spectral decomposition. These are the eigenvalues, and these are the eigenvectors. So this means that H, E, J is going to be EJ, with J equals 0, 1. Now, this forms, because of their theorems that you studied already in quantum mechanics, this is, for a two-dimensional quantum system, this gives you a full basis, which means that I can always write my state in the following way. Square root of 1 minus P E0 plus square root of P e to the I phi E1, right? And I can ask, obviously, what is the geometry of the time evolution that the Schrödinger equation gives me on either this space, for example, on the sphere, or on this space here on the block square. And as you'll see now, the evolution for in P-phi core, it's, I mean, this is it's a two-dimensional state space, so it's easier either way. But there is a reason why these are much simpler coordinates, and the reason is the following. So Schrödinger's equation is E h bar d psi over dt equal h psi. So what do? We project on the eigenbasis of the Hamiltonian, and so you get the following: E h bar d square root of 1 minus p over dt is equal to E0 h psi, which is E0. This is an eigenstate, so this is E0, and then you have square root of 1 minus p. And the same thing is true for the other one. So this for the p1, so this means eh bar d square root of p over dt is equal to E1 square root of p. What this means is that these coefficients here, as a function of time, they evolve in the following way. Psi of t, so time dependence, is going to be square root of 1 minus p e to the minus I over h bar, E0 t minus t0, E0 plus square root of p e to the minus E1 t minus t0 E1. So we see right away that the time evolution basically brings us outside basically the realm of the decisions that we made of keeping this coordinate real, right? We could have made the decision of keeping this coordinate real to identify the state space. But of course, what we can do, we know that at each time step, this is basically equivalent to square root of 1 minus p E0 plus square root of p e to the minus I over h bar E1 minus E0 t minus t0 E1. So you're seeing that right away we have one important fact, that is p of t is just p of 0. P does not depend on time, it's a conserved quantity. And then I have a phi here that I forgot. There's an e to the I phi. There you go. Then you have phi of t is just phi of 0 minus I over h bar. And actually, I'm going to call it minus omega t minus t0, where I'm define omega as E1 minus E0 divided by h bar. Right, so what you have is basically in the block square, if this is p and this is phi, the evolution is very obvious what's happening. It's like this, right? It's a straight line just going in along phi, and p is never changing. Now, the reason why this is important is because and this is not a mathematical proof by no means, but this is a suggestion to work out the details on your own. But the geometry of this solution can be encoded in a pair of differential equations, which are the following. P dot equals 0, and phi dot equal what? There's a minus sign. Yes, phi dot is minus omega. Now, if I write, how do we derive? Now, obviously, we can take the standard route, but the goal is to, show you that this is actually Hamilton's equation of motion in disguise. And the reason why this happened is the following. If I take my Hamiltonian and I ask what is the generic function of its the expectation value on a generic state, it's going to be this, right? And I can compute it in p phi coordinate, and it's going to be just E0 1 minus p plus E1 p. And I can write it as E0 plus p E1 minus E0, right? And now I can just show you that if I impose Hamilton's equation of motion on this, I get this. So let me call this as E of p. This is a function E of p that I'm going to understand has a classical Hamiltonian on this space. So I have two coordinates, and my equations of motion, therefore, are going to be what? P dot is equal dE over d phi, and phi dot is going to be minus dE over dP, right? And remember, this is essentially the equivalent of x dot is equal dH over dP, where this is momentum. Let me call this m, and m dot is minus dH over dx, right? So these two are analogous to each other. Now, what happens? What happens here is that because EP does not depend on phi, then d over d phi is equal to 0, and we get p dot is equal dE over d phi is equal to 0. First equation, and then you get that phi dot is equal to minus dE over dP, which is minus E1 minus E0, and I have there are some subtleties here, because obviously there is h bar, but working in coordinates in which h bar is equal to 1, this gives you, this is exactly minus omega. Phi dot is equal minus omega. And so you can see, now this result, you can ask, like, all right, you just show me one very particular example, and so this might not be true in general. Now, it turns out that it is true in general. If you look at p phi coordinates for a general finite dimensional quantum system, and you compute, you try to evolve and compute the results of the solution of Schrödinger's equation, you're going to realize that in probability phase coordinates especially, but this is going to be true in general, the geometry of the evolution given by Schrödinger's equation is Hamilton's equation of motion in disguise. So in some sense, the way a quantum state evolves on the quantum state space is geometrically exactly the same. It has exactly the same geometric rules, has the state of a classical system that evolves in phase space. And to me, this is really highly counterintuitive. Now, there are a lot of subtleties and things. It's not like, oh, we just proved that classical and quantum mechanics are not the same. No, there are a lot of aspects that are involved here. But what I want you to, we're already over time. So what I want you to get from this are two things. First, the geometry of the dynamics of the unitary dynamic on a quantum state space can be described by Hamilton's equation of motion, classical Hamilton's equation of motion, with a certain Hamiltonian that is basically borrowed from the linear algebraic formulas, being the expectation value of my Hamiltonian, the function of the expectation value of my Hamiltonian as a function of the point in state space. This is the first thing. And the second thing, and this is actually the thing that we're going to go deeper into in our next lecture, is that as we discussed before, I've hinted that these are Hamilton's equation of motion. So the natural kind of consequence is okay, then this means the P and phi are canonically conjugated coordinates, exactly as it happens that in classical mechanics, when I have, when I have X and P, they are canonically conjugated coordinates, which is why they have Hamilton's equation of motion. That is going to be true for quantum systems as well. And as you'll see, the point is that what you're doing when you're writing, when you're looking at a quantum system like this, or even on the block sphere, is that you're codifying the quantumness of your system into the geometry of a state space. And I find this picture to be absolutely beautiful. And there is an argument, and we'll go through it, to be made. Basically, you can check and you can see that all the weirdness of quantum mechanics, they just arise because of the geometric rules in this quantum state space that, as we'll see in the next lecture, is going to be a complex projective space. But really, it's just a phase space. It's a bit of a weird phase space with specific geometric rules and specific notions of distance and a bit more. But really, what you're doing is that you're saying, okay, I have quantum mechanics for finite dimensional quantum systems. This can be analyzed with classical mechanics on a phase space, but it's not just any phase space. It's a phase space with specific geometric rules, like specific notions of distance. And I'm referring, for example, to the question that was asked about, identifying lines and kind of bending this sheet to create a sphere. This is just, a way of explicitly saying in words that the geometric rules that govern the behavior in phase space, they're not as neat and clean. They're not as simple as it happens for classical systems. But this is actually what makes quantum mechanics different from classical mechanics and a lot of fun as well. All right, so I'm gonna end here. This was a very basic lecture, so please do reach out to me with either questions, or if you want to tell me, this was too easy or this was too hard because I jumped some step. I'm absolutely willing to take feedbacks. And yeah, I hope you enjoyed the lecture. And yeah, I'll see you next week.
Yeah, thank you very much, Fabio. It was a really nice introduction to the topic. I don't know if Ilya and Camille wants to guide us through the Q&A session. And please, since we are not so many, everybody is most and welcome to raise the hand and ask a question or make a comment or reply to the question of Fabio, who would like to have some feedback. But I think personally, Fabio, that the level was just perfect for the first lecture, and I'm sure you will engage some higher gear as the months goes along. Yeah. Right. I see there is a raised hand. Okay, and Ilya has already sorted it out. Ilya, I leave this business to you and Camille.
Okay. Ramya, you can unmute yourself and ask a question.
Oh, sorry. I think I pressed the button on accident.
Okay.
Okay. Okay, you can still ask a question if you want.
I think Jean.
Here we go.
Yeah, sorry. So for that last part with Hamilton's equations, it reminds me a lot about the theorem that says expectation values evolve classically as long as your potential has quadratic or lower order. Your potential is of quadratic or lower order. Is it the same kind of thing here, or
no,
is it
actually,
a bit more general?
It's not. It's it's so okay. Two answers to that question. The first one of physical nature. It's not the same thing. It's actually very different in the sense that I can cook up weird initial states where you know, the evolution of the or weird situations where the evolution of the expectation values have really very little to do with what happens in classical system. That's with respect to the kind of Hermfest theorem. There's a point about so this is something that has to do with any evolution, right? So this is the fact that you have Hamilton's equation, classical Hamilton's equation motion with probability phase coordinates, or in more general cases, even on the sphere, has nothing to do with initial states, has nothing to do with the way you choose the Hamiltonian, this is, I mean, it's just given to, like, it's like somebody hands you quantumness and this is what it is, right? So this is nothing to do with specific situations or, you know, cases at hand or h bar going to 0. In fact, there is no, you know, here h bar is equal to 1. There is, so in this sense, classical, in the sense in which I've used classical in this setup, has nothing to do with h bar going to 0. It's classical in the sense that the rules are the same as in the classical phase space. So you have x and p, and as I've hinted, there are canonical conjugated coordinates, and so on and so forth. So no, it's very, very different. But the reason why Hermfest theorems works for quadratic Hamiltonian, it's actually very similar to the reason why you have these kind of behavior mathematically. Is very similar to the reason why you have these kind of behavior in geometric quantum mechanics, and it has to do with the fact that Hamiltonians in this situation are quadratic. And what I mean with quadratic is that, if you remember, I've said that the notion of Hamiltonian that I'm using is the expectation value psi of the Hamiltonian operator as a function of the point in state space. But because my coordinates are the elements of the vector, and I have two vectors, you know, I have a ket and a bra. So this Hamiltonian, you can think of it when you write it in complex coordinates, it's going to be a quadratic Hamiltonian. And so the reason why it works in both cases is because of this relation with quadratic Hamiltonian. But physically, it's a very different reason.
Thank you.
Thank you. I don't see, unless Ilya and Camille correct me, I don't see any other urgent questions at the moment, Fabio. So it is then my pleasant task to thank you very much for the first introductory lecture of your mini school series. And just a reminder to the participants that we will continue with lecture number 2 next Wednesday at the same time, at 4 o'clock South African time, a little bit earlier for Fabio on the West Coast. And you can still use the same link that you used today, but I think automatically you should receive the reminder with the link and everything 1 day and 1 hour before the webinar starts. Yeah. So thank you very much, Fabio.
Thank you. Thank you for having me.
In particular, thank you, Camille, for introducing us to Fabio. That's really very kind. And my personal apologies, because at the beginning of the webinar, my internet died. And there was nothing that I could do. Yeah, I'm not sure why. Yeah. Anyway, thank you very much, Fabio, again. And we will see you latest next week. Thank you.
Yeah.
Thank you.
Bye.
Bye, everyone. Have a good evening and stay safe.